Python AST. The pyramid analogy. Top layer, interface, AST module. The interface exposed to Python programmers, allowing access to the nodes created by _AST. Middle layers, structure, _ASTC module. Guided by the parser/python.asdl file, crafting the actual node classes, providing shape and stability. Base layer, foundation, AST class. The cornerstone upon which all other elements are built, supporting the entire structure. The fountain analogy. Flow of water, AST nodes. Sprouts, AST module. Fountain sprouts re-export the water, AST nodes, making them available to different parts of the garden. Fountainhead, _ASTC module. The water source continuously generates fresh water, AST nodes, based on the ESDL blueprint. Inheritance. Fountains channels symbolize inheritance paths, guiding water, AST nodes, through various routes. Source, AST class. Fountain basin. The base basin collects and holds all the water, AST nodes, representing the AST class. The pyramid and fountain analogy, understanding Python's AST implementation. Introduction. Python's abstract syntax tree, AST, implementation is a sophisticated system with multiple layers that interact in a structured manner. To grasp how these components connect, we can use two intertwined analogies, a geometric pyramid and a fountain. These analogies help illustrate the layered nature of AST implementation, inheritance, and re-exportation, and how developers manipulate and interact with AST nodes in Python. The pyramid analogy. Imagine a pyramid with multiple layers, each representing a different aspect of Python's AST implementation. The base, foundation layer. Base layer, foundation, AST class. The broad base of the pyramid represents the AST class. This class serves as the fundamental building block for all other node types. It is the foundation upon which the entire structure is built. Middle layers, structural layer. Middle layer, structural, _ASTC module. The middle layers of the pyramid symbolize the _ASTC module. This module, constructed using the blueprint provided by the ASDL, Abstract Syntax Description Language, file, creates the actual node classes. These layers form the intricate and interconnected structures that define the pyramid's shape and strength. Blueprint layer, ASDL file. Embedded within the middle layers is the blueprint layer, representing the parser/python.asdl file. This file dictates how each node in the structural layer is formed, much like architectural plans detail a building's design. Top layer, interface layer. Top layer, interface, AST module. The pyramid's top is the AST module, the interface exposed to Python programmers. It allows access to the nodes created by the _ASTC module, re-exporting them for use in Python programs. Visualizing the pyramid. Base, AST, the broad foundation supporting all other elements. Middle, _ASTC module and ASDL file, the complex structure formed by the _ASTC module, guided by the ASDL blueprint. Each node type, e.g., SDMT, expr, function def, is part of this structure. Top, AST module, the accessible surface that allows interaction with the underlying structure. This is what Python developers use to manipulate and interact with AST nodes. Interaction and connectivity. Base to middle. The AST class provides the foundational properties and methods that other node classes inherit. Middle to top. The _ASTC module uses the ASDL file to define specific node types and structures. These nodes are then re-exported through the AST module, making them available to the programmer. Top to code. Python code written by developers interacts with the AST module, utilizing the nodes created by the _ASTC module, based on the structure defined by the ASDL file and built on the AST foundation. The fountain analogy. Extending the pyramid. To extend the pyramid analogy and incorporate the concepts of re-exportation and inheritance, imagine a fountain where water represents AST nodes and their manipulation. Fountain structure. Source: AST class, fountain basin ***. At the fountain's base is a large basin representing the AST class. This basin collects and holds all the water, AST nodes, that flow through the fountain. Routes and channels, inheritance, fountain's channels. Rising from the basin are multiple channels, symbolizing different paths or routes, inheritance, through which water, AST nodes, can flow. These routes are shaped and defined by the inheritance relationships between different node classes. For example, AST binop inherits characteristics from AST.expr. Fountainhead _ASTC module, water source ***. At the fountain's top is the water source, symbolizing the _ASTC module. This source continuously produces fresh water, creates AST nodes, based on predefined patterns and blueprints, ASTL file. Sprouts and jets, AST module, fountain sprouts. Sprouting from the channels are smaller openings, sprouts, symbolizing the AST module. These sprouts re-export the flowing water, AST nodes, from the fountainhead to various destinations, Python programs, where it can be used and manipulated. Flow of water, AST nodes. Water generation. The _ASTC module continuously generates new water, AST nodes, based on the ASDL blueprint. Flow through channels. Water, AST nodes, flows through different channels, inheritance paths, shaped by the AST base class and specific node types, SDMT, expr, etc. Exportation. Water sprouts, re-exportation through the AST module, distribute the flowing water, AST nodes, to different parts of the garden, Python programs, where developers can interact with and manipulate them. Interaction and manipulation. Manipulating water, developers interact with the sprouts, AST module, to redirect and manipulate the flowing water, AST nodes. Channeling flow. Inheritance determines the characteristics and behaviors of the flowing water, AST nodes, as it moves through different routes, node types. Foundation stability. The basin, AST class, provides stability and foundational properties that all water, AST nodes, share, ensuring coherence and consistency. Practical example, inheritance and manipulation. Consider a practical example where you want to apply a specific transformation to a certain category of nodes within an AST. You can leverage inheritance to achieve this. 1. Define a custom node transformer. Create a class that inherits from AST.nodeTransformer. 2. Override methods. Override methods to specify transformations for specific node types. 3. Apply the transformer. Use the custom transformer on an AST to modify nodes as needed. This process is akin to adjusting valves in the fountain to redirect water flow, transforming how it interacts with different parts of the garden. Summary. The pyramid and fountain analogies help visualize Python's AST implementation. The pyramid illustrates the layered structure, the foundational AST class, the _ASTC module built using the ASDL blueprint, and the AST module interface. The fountain emphasizes the dynamic interaction, the flow of water, AST nodes, through channels, inheritance paths, and sprouts, re-exportation, allowing developers to manipulate and analyze the AST effectively. Inheritance shapes the paths through which AST nodes flow, and re-exportation via the AST module provides access and manipulation capabilities to Python developers, ensuring a robust and accessible structure for parsing, compiling, and executing Python code. To illustrate the practical example of applying a specific transformation to a category of nodes within an AST abstract syntax tree using inheritance, here's a detailed Python code example. This example demonstrates the pyramid and fountain analogies and shows how to define a custom node transformer to manipulate AST nodes. 1. Define a custom node transformer. Create a class that inherits from AST.node transformer. This class will be used to transform specific types of nodes in the AST. Import AST. Class custom transformer, AST.node transformer. We define custom transformer which inherits from AST.node transformer. The override of the visit_binOp method happens implicitly when the custom transformer class, which inherits from AST.node transformer, defines its own visit_binOp method. By defining visit_binOp in custom transformer, we override the default behavior of the visit_binOp method from the parent class AST.node transformer. Inheritance. Custom transformer, AST.node transformer, sets up custom transformer as a subclass of AST.node transformer. Method override. The method visit_binOp, self, node, defined within custom transformer is an override of the visit_binOp method in AST.node transformer. When custom transformer is used, its version of visit_binOp is called instead of the one from AST.node transformer. Import AST. Class custom transformer, AST.node transformer. Def visit_binOp, self, node. Hashtag if the binary operation is addition, change it to subtraction. If isInstance, node.op, AST, add. Node.op equals AST, sub. Return self, generic_visit, node. Override the visit_binOp method to specify the transformation for binary operation nodes. In this example, we are transforming addition operations into subtraction operations. Override methods. The visit_binOp method uses isInstance to check the type of operation. If the operation is addition, it is replaced with subtraction. Let's backtrack for further clarification and understanding. We will discuss in depth. Traversal. Method overriding. The function visit_binOp, subclass versus superclass, is instance function. When we traverse an AST, we visit every node, e.g., expressions, statements, to perform operations such as analyzing, transforming, or extracting information. In our custom transformer example, traversal happens as follows. Start at the root. Begin at the root node of the AST. Visit each node. Move through each node in the tree, such as functions, operations, and literals. Apply transformations. For each node, check its type and apply any specified transformations, e.g., changing an addition to a subtraction. Continue to child nodes. After processing a node, continue to its child nodes and apply the same steps recursively. Class custom transformer, AST.node transformer. Def visit_binOp, self, node. Hashtag check if the operation is addition and change it to subtraction. If is instance, node. Op, AST, add. Node. Op equals AST, sub. Hashtag continue to visit child nodes. Return self, generic_visit, node. In the custom transformer, the visit_binOp method is called during traversal whenever a binary operation node, binOp, is encountered. Visit_binOp is a method, function, defined within the custom transformer class. It is responsible for visiting and transforming binary operation nodes, binOp nodes, within the abstract syntax tree, AST. Continues traversal. It calls self, generic_visit, node, to ensure that other child nodes of the current node are visited and potentially transformed. Line 1. Class custom transformer, AST.node transformer. Defines a new class custom transformer that inherits from AST.node transformer. Line 2. Def visit underscore bin op, self, node. Defines the visit underscore bin op method in the custom transformer class. This method is called when a bin op node is encountered during the traversal of the AST. Line 3, if is instance, node. Op, AST, add. Checks if the operator of the binary operation is an addition. Line 4, node. Op equals AST, sub. If the operator is an addition, it changes it to a subtraction. Line 5, return self, generic underscore visit, node. Calls the generic visit method to continue traversing and transforming any child nodes of the current binop node. The visit underscore binop method is a custom visitor function that transforms binary addition operations to subtraction operations in an AST. It overrides the default behavior provided by the AST node transformer class to achieve this specific transformation. Method overriding. Technique. Method overriding is a technique used in object-oriented programming to modify or extend the behavior of inherited methods. Function. The overridden method itself is a function defined in the subclass. How method overriding works. Superclass definition. A method is defined in a superclass. Subclass override. A subclass defines a method with the same name, parameters, and return type. This new method overrides the superclass method. Invocation. When the method is called on an instance of the subclass, the overridden method in the subclass is executed instead of the one in the superclass. Visit underscore bin op is a method, function, defined in the AST node transformer superclass. By defining visit underscore bin op in custom transformer, we are overriding this method. Superclass. AST node transformer has a method visit underscore bin op. Subclass. Custom transformer inherits from AST.node transformer. Override. Custom transformer defines its own visit underscore bin op method, which overrides the method in AST.node transformer. IceInstance is a built-in Python function used to check if an object is an instance of a specific class or a tuple of classes. It returns true if the object is an instance of the given class or any of the classes in the tuple. Otherwise, it returns false. Object, the object to be checked. Class info, a class, type, or a tuple of classes and types. IceInstance. Node, op, AST, add, checks if node, op, the operator of the binary operation, is an instance of AST, add, an addition operation. If node, op is an addition operation, it is replaced with AST, sub, a subtraction operation. Why, generic. The term indicates that this method does not perform specific actions on nodes, but instead visits all children of a node in a generic way. Purpose. Generic underscore visit provides a generic way to visit all the children of a node, ensuring the entire AST is traversed. Usage. In custom transformers, generic underscore visit is used to ensure that after specific transformations, the traversal of child nodes continues, allowing further specific transformations to be applied if needed. Check and transform, if is instance, node. Op, AST, add node. Op equals AST, sub, checks if the operator is addition and changes it to subtraction. Continue traversal, return self, generic underscore visit, node, ensures that after transforming the current node, the traversal continues to its child nodes. Generic underscore visit is an actual method provided by the AST node transformer class in Python's AST module. It is not made up. It is a built-in part of the Python standard library used for traversing and transforming abstract syntax trees, ASTs. Generic underscore visit in AST.node transformer. In the context of the AST module, generic underscore visit is used to handle nodes that do not have a specific visitor function defined. It allows for a generic way to traverse the tree, ensuring all child nodes are visited. You can find generic underscore visit in the Python documentation for the AST module. AST.node transformer. AST.node visitor, which also uses generic_visit in a similar way.